Hi. Okay. So in this last part, we'll be looking at a few example simulations. I have written the um, question first, and then I have just went out and okay. So these are just textbook solutions. So I've just copied them here, and so I'm going to discuss them. Um, and they're written in R. So most of them I've written in R. Some of them are intuitions. So I've not shown the R code there, but you should get it in the textbook. So let's just talk about this. And if you have any questions understanding any part of the code, let me know. So the first thing is you're given a board with two boxes on each side with a numbering from 0 to 7. Players token advances around the player starting at 0. Two types of plays that it rolls, you get 1 to 6 on the die. And the other one is you get a bonus turn. So you get the bonus only if you have landed on 3. So if I'm on square 3, I would get another turn, right? So you have to find the probability that if the player is at box number 4 right now, what is the so given that the player is at box number 4, what is the probability that they got a bonus? So when you think about it, let me draw it for you so that you have a better understanding. Um, all right, so I should have had a picture of this while I was recording, so I'm sorry for that. But just think about this. This is the game you have. You have 8 boxes, 2 on each side. It starts from 0. So you go from 0, 1, 2, 3, 4, 5, 6, and 7. So the thing is that you start from 0, you roll the die 1, that is the die, the roll R. And then the next time you can get a bonus if you land on 3, right? So if you go on 3, you get a bonus. All right, so that's the thing. And we have to show that if what is the probability that if I'm at 4 right now that I had taken a bonus turn, right? I'll just use the pointer again. All right, so this is how you define the function. Board sim is a function. Argument is the number of repetitions. Now the number of repetitions is like the number of times you want to run the simulation. So that's 10,000, 1,000 or 10,000, depends on what you want. It's usually good to have something around 10,000 or 5,000, 10,000 repetitions. All right. So this is a counter that is set to 0. This counter is to count the number of times I will land at 4. Okay. So count the number of bonus given 4. So this is a counter to identify the number of times that the counter was given. So the bonus was given and I ended at 4. Okay. So two counters, count 4, the number of times I am at 4, and count bonus given 4, that is the number of times I'm at 4 given the bonus. Okay. So this is for I in, so this I would run this loop for n reps time, that is number of repetitions that are there. I get a sample that is just one value, the position from 1 to 6, I'll get one value, right? So if the position is 3, I get the bonus, that is true. Now, if the position, I get another position that, and I try to sample it again, that is, this is the bonus turn here, right? So this position was, I was at 3, I got the bonus. Did I get 1 or not, right? So, and this is like modulo 8. So this is a modulus. I didn't cover this in the previous section actually. This is a modulus function or an operator, sorry, not a function, it's an operator, right? So if position is not 3, the bonus is false. If position is equal to 4, then, so this is it, this is ends it. This if else condition ends right here. The if condition was if position is 3, I'll get the bonus and the position changes now, okay? Else the bonus is false and nothing matters. Now if the position is 4, then I add the counter, I increase the counter, that is the number of times I landed at 4. And here I check if the bonus is true or false, that I set it right here. If the bonus is true, the count bonus given 4 will increase again. And I return count bonus given 4 upon count 4. So that is the number of favorable outcomes upon the number of total outcomes, right? Things to look out for in this code. This is how you write the function. This is the function name. This is the keyword function that defines it as a function. Number of arguments. I have had two counters. One to count the number of times bonus is given that I landed at 4, and the one is the number of times I landed at 4. Another is sampling the die throw. So it is sampling the number of die I threw. So 1 to 6, so it gives a response from 1 to 6, and just one value out of that, right? If I had given 2 here, I would have 2 values out of it. So I don't want that, I just want 1. So that's it, and I added the bonus here. And this is your example for a simulation that the board game problem in the textbook. The next one is a rolling dice problem. So if we roll 3 dice, what is the probability that the total is 8? Right, this is the first simulation I think of the textbook. So yeah. All right, for this, I have 3 die. I roll the 3 die. What is the probability that the total is 8? Again, very simple. We define a function, probability that the sum is equal to k. K is 8, right? So this is the number of times I want to throw the die. Total is the total I want, so that is 8. And n reps is the number of repetitions I'll be running. Count is 0 again. It's a counter to find out the number of times I get it. Get the sum as 8. I run this loop n reps time. Initially, the sum is set to 0. So this is like for every simulation. Every time I throw a die, the sum is 0, and I add the 3 numbers, right? So here, as you see, the number of dice that I have, right? So I'll be running this loop again and again. So I'll be rolling a die. I'll be rolling a die for rolling every die. So I'll get a value out from this function right here. That this returns a sample value from 1 to 6. This is supposed to be a colon right here. So it's 1:6, 1. So this is wrong right here. It's going to be 1:6. So from 1 to 6, I get one value for this sum. I run it for 3 times. If the sum turns out to be 8, the counter goes up. Otherwise, it stays the same. So essentially what I'm doing is I'm running a function for in which there is a loop that runs for n repetitions. That is the number of times I'm sampling it. Each time I sample the die throw, 3 dice. Okay, so the number of dice I have, I throw them again and again. And I sum the 3 dice. The value I get, if it is equal to 8, the sum of them is equal to 8. The counter increases, otherwise it stays the same. And hence I can return the probability, that is the number of favorable outcomes upon total outcomes, that is the sum. The number of times it is the counter sum. So sum is a counter here that it is equal to 8. And this should have been 8 and okay, so I'll repeat count upon n reps. This is the second type of solution that was given in the textbook. So what they did here is function probability sum, total value, number of repetitions. Here what they're saying is that the sum is a vector of length n reps. So what they're doing is for every repetition they're making a vector of the length of the number of repetitions I'll be doing. And they'll just store the sum in each one of them. And whenever the sum is equal to the total, that is what you want. That they'll return that value. Okay. So that is that. It's pretty similar to the earlier one. So anyway. The second one is that they replicate n reps. So this is just efficient code writing. It's nothing, it's the same concept that they have a vector of size n reps, the number of repetitions. And for each element, they'll call in this the sum of roll num, that is 3 times the value that they keep on getting. And that's what they do. The next question is a bus ridership problem that is again in the textbook, where they say that at each stop, a passenger leaves the bus with a probability 0.2. At each stop, 0 passengers enter with the probability 0.5, 1 passenger with probability 0.4, and 2 passengers with the probability 0.1, right? So There is a 20% chance that somebody would get off, 50% that a person would get off, no person would get on, 40% that only one person, and 10% that only two people would get on. Okay. Initially, the bus was empty, so we need to find the probability that at the 10th stop, the bus is empty. So this would be a little tedious, but let's look at it. So we have the number of repetitions, that is 10,000, number of stops is 10, count is 0. So you're looking at the 10th stop. For I in the number of repetitions, this loop is totally for the number of repetitions. So we'll not look at that because that's what we looked at in the earlier examples. Initially, the passengers are 0 for j in. So this again is for the number of stops that we have. If passengers are greater than 0 for k in 1 to passengers, would they get off or not? This is what we'll be calculating here. Run if 1 is less than 0.2. So run if actually gives you a value between 0 and 1. And if that is less than 0.2, that is a passenger leaves the bus, then we'll be decreasing the count by 1. And now here we calculate the number of new passengers that will be joining us. So that will be sampled between 0 to 2. So here, this is what I was talking about in the one when I introduced the function sample, the weights, the probability weights. So for a person to get on, so from 0 to 2, there are 3 elements, 0, 1, and 2. And probability that 0 would come in would be 0.5, 0.4 is the probability for 1 to come, and 0.1 is the probability for just one person, for 2 people to come in. Right, so this is what is sampled here. Just one value will come out of them with the probability weights that are given. And the passengers will just be added by the new passenger and just keeps on going till the number of stops, so that is 10 stops. At the end, we just want to see if the passengers were 0 or not, and increase the counter. And we return counter upon the number of repetitions. That's what they did. So just 2 things to look here. The first one is the sample function here that you gave in probability weights. And you did there were 2 events, leaving the bus and getting on the bus. So leaving the bus was handled by this function right here for every passenger. So that's the passenger leaves the bus, right? So every passenger gets this chance and they can keep on decreasing it for k values. Okay. Coin toss until the kth heads come. So we toss the coin until we get k heads in a row. Let n denote the number of tosses needed, so that, for instance, the pattern HT, HH gives n is equal to 5 or k equal to 3. So 3 heads came in a row, right? So k heads come in a row. We define the function. Counter is 0 for repetitions up till n reps. We have another counter is set to 0 for now. For 1 till m, we toss every time, and the toss is 0 or 1, heads or tails. Now we keep on tossing it, and here we increase the counter again if the toss is 1. So that's if it is a head, we keep on increasing it, and if it is equal to the number of repetitions we want, so we want k to be 3, so that 3 consecutive heads. If that is 3, we break it. Otherwise, it keeps on moving on and on, right? So if consec is less than k, counter is again added to +1. Okay, that's again the same thing. So like you keep on rotating it, like keep on iterating it till you get 3 consecutive ones. If it changes, you move on to the next one. Oh, broken rod problem. That a grass rod drops and breaks into 5 pieces. If the rod was 1 unit in length, what is the probability that the shortest piece is smaller than 0.2 units? Again, a simple thing. We have the whole thing. We break it. So we just run a run if statement, which breaks it into 5 parts. And the number of times you have a broken part is so we find the minimum of the run if statement, and the number of times the minimum is less than 0.2. That is, the counter keeps on adding that +1. That's all that it does. Here what we do is, so that was the intuition. Here what they've done is they use the third concept, the third type of solution in the dice problem, where you just replicate a whole array of n reps, and you just call the function min piece for k times, and that's it. Just want to discuss something about the Aloha network. What the Aloha network does is, there is a central computer. I'm the central computer. There are 10 students around me, and all of them are trying to reach out to me in the audible frequency range. I can listen to one of them at a time, and that makes sense to me. But now, if all the 10 start to talk to me at the same time, it wouldn't make any sense to me to hear anything, right? So that is what collisions are. What happens is that is exactly what my intuition about the office hours is. Like I have 2 hours of time. If everybody wants to come in at the same time, then I won't be able to cater to any one of them. Instead, I'm giving a slot to each one of the students. So yeah, so that's called backing off. Like the nodes back off communication transmission sometimes with a certain probability, right? So P is the probability that the person will transmit, and 1 minus P is the probability that they won't transmit. Q is the probability that they have a question to ask. 1 minus Q is the probability that they don't have a question to ask, right? What else? We call a node to be active if it has a message to send, okay? So yeah, the question was, what is the probability that, so one more thing. X1 and X2 is the number of active nodes at the end of epoch 1 and epoch 2. Epoch is just the time slot. So what is the probability that X1 is equal to 2? The only way that we have 2 active nodes at the end of the first epoch is that none of them send, or then either one of them send, both of them send, and it leads to a collision, right? So that is the probability that both of them will lead to a collision is p squared if they both send, and if they don't send, both of them don't send, that is 1 minus p squared, right? So that's just p squared plus 1 minus p squared because they're mutually exclusive. So you just add their values in. I wanted to talk about, given that x2 was 2 and x1 was 1. So given that initially, after epoch 1, we just have 1 active node, but then after epoch 2, we have 2 active nodes. So how is that possible? So I think I have like put it on Piazza as well right now at the moment. The number of ways, the probability that this would happen, that given x1 is 1 and x2 becomes 2, is that there are 2 events that happen in chain. The first one is that the one that transmitted initially now has a message, right? If it does not have a message, then the other node can just send it or doesn't send it, doesn't matter, right? So I put it on Piazza if you want to look it up. If there is any question, let me know. And that ends the discussion for today. I hope the videos do make sense to you. Some ending notes would be, yeah, for people who have just started to code in R, it would make sense to look at the tutorials. If you have any questions with any syntactical errors, just let me know. And yeah, I mean, that's all I have for today. And yeah, feel free to reach out. Thank you. Stay safe and stay healthy.